My talk tonight is about computational trust, and in particular, the evaluation of trust in terms of risk. Essentially, one of the core questions of my research has been, how far do you have to go and how much risk do you have to bear in order to establish trust? Here you can see perhaps a sales rep or someone who's trying to encourage a customer to trust him by willingly submitting to some pretty risky situations. And that's the problem with this business, that when you actually go out there in the online world, as Vijay's been pointing out, you actually are exposing yourself to a variety of risks, some of which you know about and can identify and quantify in a loose way, others of which you don't know about and aren't necessarily aware of in any way at all. In particular, as Vijay pointed out, we're now moving towards a much more complex environment in which we have ubiquitous computing. We have computers everywhere. I mean, I'm standing up here at the moment probably carrying around more computing power than a US nuclear aircraft carrier of the 1980s, just strapped to my hip in the form of a phone. So mobile phones have got a huge amount of intelligence built into them. We're finding embedded intelligence inside cars, inside white goods, in glasses. You've probably seen the Google Glasses demos. And Intel, in fact, at their developer conference last week, made the prediction that we'll have ubiquitous, almost zero energy consumption computing by the year 2020. Because the technology, the fabrication of the transistors will make them so small that their power consumption will be absolutely minimal. We're seeing the same thing with displays, for example. In addition, we're also seeing always-on networking. So these mobile and embedded devices that maybe you carry around with you or you have in the home are connected to servers out there in the cloud. And as Vijay pointed out, we also have geolocation, which means that the device knows where you are at any point in time via GPS or triangulation of Wi-Fi access points and those kinds of things. I mean, when we got here, I just flipped open my tablet and it said, oh, you're at Macquarie University. Do you want to check in and tell the world where you are? And it will do it for me automatically, which, of course, has got some corresponding risks to privacy if you don't control it properly. So now with these ubiquitous embedded devices in cars, mobile devices, etc., they can locate services for us. I mean, you can be driving along, realize you're low on petrol, and your car or your phone can contact the outside world and can find out where the nearest gas station is. Or you want to get money out, it'll find you an ATM or a coffee shop, whatever. And the next step, of course, is not just have the device inform you, because in many cases, people don't make good trust decisions. The Australian Taxation Office, for example, is suffering a whole spate of phishing attacks at the moment. People are getting emails that say, we've got your tax refund ready for processing, click here, fill out the form, and we'll credit your tax refund to your credit card. And people then click on the link, give away their credit card details, and surprise, surprise, their credit card account gets emptied. So if people aren't making good trust decisions, and we're going to have more and more trust decisions to face as we move around in this always connected world, why not make the phone make the decision for you automatically? So as you travel around, you arrive in Hong Kong, for example, Telstra doesn't have operations in Hong Kong, but they'll hand you off to some external provider, and your phone can then negotiate with different telcos in that city. You might negotiate the best rate, the best service quality for your anticipated needs. Do you want a data service, etc.? And it can pick the appropriate supplier. So, in order to make some progress towards a world in which the machines are starting to make trust decisions, I've been working on computational trust. And my work really has three primary strands to it, or three underlying concepts. The first thing was the redefinition of trust in terms of risk. My background is in the security consulting business, where we have a long history of qualitative risk assessment, really rule of thumb assessments of what the risks actually are. But there is quite a long tradition, especially in engineering, of probabilistic and quantitative risk assessment. So I went through what was happening there, because of course computers deal with numbers, and we want to put some numbers in. And as you'll see, I came to the conclusion that trust really is the acceptance of residual risk. Once you've done whatever you can do to minimize the risks in various ways and to investigate what the risks are, then you can decide to make a trusting decision by proceeding, for example. I also use Bayesian learning techniques in my work. And as you'll see in the latest incarnations, I'm evaluating transactions as a kind of probabilistic finite state automaton in which the absorbing states of the automaton actually are the various different risk scenarios. And we'll build up and get there towards the end. So as Vijay pointed out, trust traditionally has been expressed as belief in some partner's either benevolence and in ability and integrity to perform some service on which you depend. And in the socio-cognitive models, there's lots of writing about trust in psychology and sociology, management theory, etc. But it's generally been defined only in terms of probability. But in quantitative risk analysis, the risk theorists always take into account both probability and also the consequence. And by taking the consequence into account, we're able to actually, at least partially, take into account some of the context in which the decision is being made. And so, I define, therefore, trust as being acceptance of residual risk. In this diagram, you can see across the x-axis, I have the actual situation with respect to some partner agent. It might be extremely untrustworthy and will fail every transaction that you attempt to commit with it, or it might be extremely trustworthy with a probability of success of 1, for example. That's objective reality, the trustworthiness of the partner. On the y-axis, we have the trust, which is the agent's belief in what's going to happen, ranging again from 0 up to 1 in terms of probability. We'll mix the consequence in later. So as trustworthiness increases, we'd like the assessment of trust to track it ideally exactly. Of course, by observation of what's happening, we will not be able to come up with an exact measure of trust, and we'll always have some degree of error. The worst situation here is with a partner that's kind of half trustworthy, so to speak, and we are therefore seeing it on this trust threshold. We're going to place ourselves in one of these two quadrants if we're off the actual line where trust exactly matches trustworthiness. Well, we'd like to have, ideally, beyond this line up in this quadrant, where we are able to make correct trust decisions to proceed. In which case, if we engage in a transaction, we'll obviously put up some stake and we'll get back some utility because the transaction, if it's a single-step transaction, will proceed correctly. And down here, we have the correct mistrust decision, in which we decide that this particular partner falls below our trust threshold and it actually is not trustworthy enough, and we correctly decide not to proceed. We may face some opportunity cost, we may have lost a bit in investigating and trying to find out how trustworthy it was. But the worst situations to be in, are where we have these quadrants here, a misplaced trust, where we actually decide that we see it as being above the trust threshold, but in practice it isn't that trustworthy. And therefore you proceed and we're going to lose big time. And also the more subtle misplaced mistrust, type 2 error, in which case we're going to lose by attempting a transaction with an agent when we could have actually proceeded with a more trustworthy partner. So there's an opportunity cost associated with that. So if the trust decision is the explicit assumption of residual risk, then we have to tighten up what's the definition of risk. And the one that I found that worked best for the work that I was engaged in was actually in Volume 1, Number 1 of Risk Analysis, the Journal of the Society for Risk Analysis, back in 1981 by Kaplan and Garrick. And they define risk as being a whole set of scenarios, each of which comprises a probability and a consequence that flows from that scenario of loss or perhaps of gain or whatever. And we can perhaps identify all the various possible scenarios. There'll be some that we don't identify, but we know that they're typically, for example, not very likely. And so we can identify the probability of the various different scenarios arising by using Bayesian learning techniques. By observing transactions, by trying transactions, we'll build up a history using conditional probability tables, the beta distribution, the Dirichlet distribution. I'll show you the beta distribution in a minute. And of course, the interaction between the agents in terms of payment, delivery of product, etc., defines a consequence, the stake that you may place out, a price of buying something, the utility you get back from it. And these can be parsed out of XML messages in e-commerce transactions, for example. So how does the Bayesian learning work? Well, I actually have built a whole series of simulators with agents which misbehave in different ways. Some of them will misbehave sometimes. We can vary it and make them fail a lot of the time or a little of the time on a random basis. Others are consistently trustworthy or untrustworthy. And in a universe of agents, the goal is to find out which ones are trustworthy, which ones are not. And there are agents that are more complex. My agent model 3, for example, is controlled by a Markov model, and it will flip between being trustworthy for a while, then becoming untrustworthy, then flipping back to trustworthy again. And so the various different trust models I create have to try and identify these. Their behavior can be more complex. And I'm using the beta distribution for the simple cases. Let's see how that works. The beta distribution mathematically isn't very complex, as you can see. It actually is computationally quite easy to deal with, in that all we really have to do is count successes and failures. That's the basic trick. And we count our number of successes, add 1 and get a figure called alpha, the number of failures, add 1, get beta, and we can then work out what the mean of the distribution is, and that's our trust value. This is the actual probability density function of the beta distribution. And this is what it looks like, just to give you an impression of how it works. What I have here is a sequence of plots of the beta distribution, starting off with an agent that has 1 failure, so it's screwed up once, but then it behaves correctly in transactions that follow. And over time, with 1 failure, 1 success, 1 failure, 2 successes, etc., the distribution will change from being the sloping line here, then of the success, it becomes that line there. Then gradually it moves up to this end. And the idea of this is that what's the chances of the partner agent being trustworthy between 0.8 and 1? It's the area under that curve, basically. And at first, when we don't know much about it, the area under there is quite small. But gradually, as you can see, it actually increases and it peaks. And that becomes the trustworthiness value that the agent has learned. Now, how do you learn? Well, to learn behavior, you have to engage in behavior, and that exposes you to risk. That's the whole point. And so the goal here is to choose some kind of metric of performance. For example, minimizing the loss due to high-value failed transactions. And I've tried in the early experiments 2 different approaches to this. One is to simply set a threshold for the loss I can face in terms of an individual transaction. The other one is to actually work out the risk of the transaction. And it turns out that that converges faster onto trustworthy partners, because as we find that they seem to be trustworthy, then the amount I'm willing to risk actually increases, because the probability decreases of losing it. And so as a consequence, what we find is this: comparing the run length of a simulation, this is how far does it get, what state are they at, in terms of gain, that is the amount you get back for how much you spent, the risk-based analyses, which are with different thresholds, actually come up a lot faster than the ones which are consequence-based. And so using risk actually works better than a simple consequence threshold. Losses, likewise, if you measure the loss is higher for the consequence-based models than the risk-based ones. Problem is, though, how do you set the appropriate threshold for a risk decision or a consequence decision? One way to do that is to use a utility function, which shows the marginal utility of the transaction compared to your current asset base. So what happens is that if this is our current asset base, a failed transaction takes us back in terms of assets, whereas a successful one takes us forward. But we then plot that through a function that has a concave shape, like, for example, just a natural log function will do. And because it's steeper down this end when we have low assets, what's going to happen is that the damage done to us is much more than it would be when we have lots of assets. So in effect, what that does is to relate the threshold automatically to the amount of assets that the agent has, i.e. it could be money that it has to spend on services, or it could be, for example, battery life that it has to conduct whatever it needs to do. It turns out that using this technique doesn't actually maximize the return in terms of what you get back for what you've spent. But It does maximize the returns, it does minimize the losses. The major reason is that using the fixed thresholds, a lot of agents will in fact just quietly go bust. They enter what's called gambler's ruin, and they have therefore no funds left to do anything else. Whereas these ones naturally seem to get kind of stiffer, if you like, or less trusting automatically as they go back down that curve. And that actually works out quite nicely as an automatic mechanism. And this graph actually just shows the trust models that use fixed thresholds tend to experience gambler's ruin. If you give them a small amount of initial assets, they don't survive for very long. But the ones that use the utility function, a logarithmic one, for example, actually do quite well in that environment. My most recent work has focused on much more complex transactions in which we have multiple steps and stages in transaction, possibly with payments and utility being returned as the transaction proceeds. Now, the way this actually works is that the entire transaction gets modeled as a finite state automaton. So it proceeds from state to state to state based upon events, which are the messages it receives and the commands that it sends back out, the messages it sends. To model untrustworthy behavior in these, I actually use what's called a Segala automata model. In other words, there are probabilistic transitions which say, with a probability of 0.9, I will send what you've ordered or provide the service that you've requested, but of course with 0.1 I won't. I'll make a different transition and go to a different state. And so the probabilistic transitions model the untrustworthy behavior. To defend against the untrustworthy behavior, I use a kind of guarded transition scheme in which, as it goes through the various states, it will actually consult the trust model based upon its current exposure, because it automatically accumulates the amount of money it's laid out, what it expects to lay out, the returns it expects to get back, and will decide to proceed or to bail out of the transaction at that point. Each of the final absorbing states of the automaton corresponds to one of the scenarios that I mentioned earlier from the quantitative risk assessment. And the total risk really is a probability distribution over the absorbing states of the composite automaton. So what's the benefit of doing this? Well, it supports much more complex interactions. The major case study I'm working on at the moment is a very complex multi-stage scenario in which bandwidth trading goes on between different agents, and they bid to actually consume bandwidth, suppliers offer bandwidth, then it may or may not be utilized. And so there can be quite complex interactions in multiple stages in the various different interactions. It also allows composition of interactions involving more than just pairs of agents. So there can, in fact, be interactions between, for example, a supplier, a shipper, and the customer. And they can be modeled as separate sub-interactions, so to speak. We can have arbitrary definition of the outcome-related state variables. And there's also the ability to relate other factors to the risk by looking, for example, for signifiers of trust, like certifications and things like that. So the state-based trust models simply read a description of the transaction, which is expressed in a very simple language, which I've designed for the purpose. It does this actually at startup time, and it does this by creating what's called a transaction type, which is what the script represents. And that actually is the finite state machine. Then attached at the time the transaction executes, there's a structure or an object, a class, called a transaction, which contains all the information relating to that specific concrete transaction as it proceeds. And it actually then consults the various different trust models to make its trust decisions. It dynamically recalculates the risk as it goes, as the transaction proceeds, using a technique called value iteration. So it actually forecasts what's going to happen. This is the transaction type. It's actually a finite state automaton in the classic description of that. But it gets more interesting when you actually combine it with the transaction. And so here's a very simple little scenario, just to give you an indication of, make it concrete. What we'll have here is a transaction in which a shopper buys some clothing, for example, just to make it kind of easy to understand. They will send some payment, then wait for the product to turn up. If they're lucky, it just simply arrives, and it's the correct product. Right? And so they simply are happy at that point, they're satisfied. Alternatively, it might not turn up and was never received, in which case they're going to have to accept that's the end of the transaction and try and regain or recoup their investment as best they can. Alternatively, it could be received, but it's the wrong color. They might decide, well, it's just too much hassle to return it. This shade will do me, but I'm not as happy as I would be if I'd got the color I requested. Or if it's the wrong size, but now if it's the wrong size, that's no use to me. I have to return it. And so we cycle through a return state, okay, until eventually we get the final correct product. Now, it could be that they actually ship the wrong size again. So you can wind up going around this loop multiple times with decreasing probability. And the value iteration actually calculates out what the likelihood of these various different things and the consequences of them actually are. So, the final part of this is the incorporation of reputation information. When you're learning by simply performing interactions and exposing yourself to risk, it can take some time to actually learn the trustworthiness of partner agents. A better approach is to either learn by observing others, which happens exactly the same way, or by obtaining reputation information. So my model allows for the exchange of reputation information, which it incorporates into the trust models by building conditional probability tables, basically. And it subjects the reputation messages themselves to trust evaluation. Because you could actually give me reputation messages about somebody else which are spurious and fake and saying, use this agent, it's highly trustworthy, but it's not, and you're in partnership with it. It's a form of attack. Rather like the authors putting up fake reviews of their own books on sites like Amazon, for example. So it learns about effectively reputation or recommendation as a service provided and subject to trust in its own right. What I'm finding, what I've concluded so far, is that by defining trust in terms of risk, we can first of all contextualize trust decisions in a way that makes sense for relatively small devices. We can learn about partners faster than just having simple risk thresholds. We can also reduce losses during the learning phase. By relating the risk to assets via utility functions, we can avoid gamblers' ruin and achieve a longer lifespan for intelligent agents. And by modeling these transactions as automata, particularly as Markov decision processes, we can deal with much more complex, multi-step, multi-partner, multi-outcome transactions. There's some references there for anyone that wants to follow up on them. That's essentially it. Thank you to VJ. Thank you to Annabelle McIver, who's my supervisor. Thank you also to my wife, Sue, for putting up with me.